Welcome friends to the 24th lecture on module 2, where we are going to extend the discussions on mechanical models and reliability analysis. So, this is lecture on module 2, where we are focusing on structural reliability, in the online course on risk and reliability of offshore structures. If you recollect back in the last lecture, we said that mechanical models should represent as close as possible the physical phenomena or the real behavior of the element or the structure, because in many issues the random variables which are used for reliability analysis may be derived based on some experimental investigations or from mechanical models. Interestingly, we also said that one can do a simulation based synthetic data generation, where I can use either Monte Carlo simulation or perturbation techniques to really assimilate the resistance and strength offered by the material and the structural system, based on which the probability of failure or the converse of probability of failure, which is nothing but the reliability, can be easily estimated. However, while estimating reliability or doing reliability analysis, certain issues are very important, as we discussed in the last lecture. One important issue is the behavior, the resistance or the strength of the material or the structural system as a whole, which are derived essentially under experimental investigations, because certain issues cannot be actually derived based on numerical models. I will come to an example today to explain you what is exactly the difficulty when you talk about deriving certain structural characteristics or certain strength and resistance of material or members or elements in a given structural system, which need to be investigated only through mechanical models. So, mechanical model accuracies or the data required or the input variables which are fed into making the mechanical model are very strongly coupled with the reliability analysis. Now, to look at this in detail, let us say the complexity of mechanical model and reliability criteria can be done in 4 stages. So, the complexity which is connecting the mechanical model to the reliability analysis. Can be actually done in 4 stages, can be evaluated, can be looked upon in 4 levels, or let us say 4 stages. They depend on the modalities they take, okay? They depend on the modalities and they also depend on how do you define the complexity. So, depending upon the 2 factors, one can always say or express the level of complexity involved in coupling the mechanical model with reliability analysis. Let us say the first criteria or the first stage can essentially come from the external action and resistance. External, it can be action, it can be resistance also. One is the external action, which is coming from the loads or forces, other is material property, which can come from the material characteristics. The second could be internal, which can essentially come from the size of the member, from the material characteristics of the member used for the mechanical modeling. Can also look at the boundary conditions which are used for the mechanical modeling. The third could be, of course, will lead to the random variables or the randomness in the variables used for the input analysis. I call this as a first stage. The second level could be essentially from the state of loading. It can be cyclic, you are looking for the characteristics or the strength and resistance properties under cyclic loading. You can also look at the same system from dynamic loading perspective. On the other hand, you can also see what is the effect of these on the input variables which are used for mechanical modeling. So, that could be the second level of complexity. The third level of complexity essentially comes from the method of analysis or method of modeling. Let us say linear, you can look for a linearized modular assumption, you can also look for elastoplastic material characteristics. It means you can estimate or attempt to estimate the resistance characteristics of the material or the member on elastoplastic stage. One can also look at non-linearity, which can be either arising from the material non-linearity or it can be even arising from geometric non-linearity. So, one can feed these as input data to the mechanical model, which is also one of the important variables in doing the reliability analysis. So, that is the third level of coupling we have. The fourth level could be arising from the internal strength and resistance characteristics, estimate of internal strength and resistance characteristics. Complexities can arise essentially come when you are able to locate these explicitly or implicitly. One can also comment upon whether the internal strength and resistance is smooth or not. I mean, is it easily arrivable, whether the internal resistance has a strong curvature. This can be very effective when you are talking about the moment resistance characteristics of a given system. Essentially, then you look at the selection of performance function, which essentially depict the correct behavior of the internal strength and resistance. That is the fourth level of complexity what we have in case of the mechanical modeling and the reliability analysis coupling. Now, in such analysis, complexities arise in coupling the mechanical model to reliability analysis. So, there are other important factors which can also govern other than these 4 levels of complexity. Other important factors could be time variant properties of both load and material. The second factor could be the degree of approximation which is being used in the level of analysis. The third factor, which could be whether we are including the second order effects, inclusion of second order effects that arise essentially from the geometric and material non-linearity. Further, the factors could be choice of an appropriate limit state function, and choice of an appropriate probabilistic model, because in the last lectures we could see what kind of distribution or probability density function can represent invariably the best way of expressing the random variables, Weibull distribution, Gumbel distribution, etc., which we discussed in the last lectures. So, choice of appropriate probabilistic models is again another factor which will govern the coupling between the mechanical model and the reliability analysis. Interestingly, one can also include of aging effect, which causes material degradation due to age. But of course, very difficult to include this in the mechanical model. But interestingly, all these factors in particular, in general, let us say in general, and this factor in particular affects the results of reliability analysis significantly. So, essentially one should be able to capture the effect of all these factors which will amount to the coupling between the mechanical modeling and the reliability analysis as close as possible, because if you look at all these factors closely, these are actually true depiction of the physical behavior of the system or the material in terms of its behavior under the given state of loading, which is going to be represented in the mechanical model, of course, to scale. Now, the issues here are, can we actually have a system or an example by which we can clearly show how at least one of these factors can be affected very seriously, which will become a very important input as a random variable in the reliability analysis. Friends, let us try to recollect that reliability is actually a study which tells us to know whether the system is successful in performing the intended function under the given space of time, under the given loading or under given specified conditions. So, one should be able to check the system for its safety or for its success in performing an intended function. So, the system's performance is assessed with input random variables in the reliability analysis, which can be sometimes derived directly or sometimes can be derived indirectly through the mechanical testing of the system, structural system or the material. So, we are talking about the coupling between the mechanical models which are required for deriving the input variables for input random variables for the reliability analysis. So, many factors do affect it significantly, but in particular the aging effect, which is very important in offshore structures, because material degradation takes place under the corrosive environment present in sea states. So, this need to be modeled or this need to be captured, or the degradation of the material strength and resistance with respect to age should be a very important valuable input as a random variable in the reliability analysis, because this will now govern the strength or the safety or the success of performance of a system in with respect to time. That is important. We already saw that time and space both cannot be handled in a stochastic process. We can always replace the space event and we can always handle only the time event. So, it is important that the material degradation effect, which is one of the time factors, should be included in the mechanical model as far as possible. Even though there are few limitations existing in mechanical modeling of form dominated offshore structures, however, it is very important that we should examine them without any approximations. So, the complexity is more in offshore structures in particular, because offshore structures are generally form dominated. We can give a very interesting example. We all know that, for example, let us say an FSRU, a TLP, a spar, a triceratop, which are compliant or floating offshore structures. Essentially, they are designed in such a manner they remain positive buoyant. Therefore, the installation, commissioning, erection and decommissioning becomes easy and the installation cost is as low as possible. So, the form dominated systems need to be carefully modeled in the mechanical systems, so that the input variables which will govern the failure state of these systems should be correctly depicted in the reliability analysis. So, it is very evident and important that the form dominated properties of offshore structures should be modeled in mechanical systems without any approximations. Let us take one specific example and illustrate this example with this complexity. You know, hinged joint is one of the classical example which can be quoted, that cannot be modeled completely in sense of its performance behavior under the given load combinations. Now, one can ask me a question where hinged joints are very effectively used in offshore structures. For example, if you talk about articulated towers, if you talk about triceratops, etc., you can see that these are the places where a single point failure is investigated in the form dominated designs in this. Let us take up an example of an offshore triceratop and show you or try to illustrate what would be the influence of a wrong modeling of this in reliability analysis very quickly. Okay. So, now interestingly, triceratop is a relatively new geometric form which is essentially extended for deep water and ultra deep water oil exploration. Kindly pay attention to the figure shown on the screen now. The figure typically shows an offshore triceratop where the plan is shown on the left hand side, and the elevation is shown on the right hand side of the figure. So, essentially a triceratop consists of 3 legs which are called buoyant legs. So, these are the 3 legs of specific diameter which are called buoyant legs. These 3 legs are not interconnected to each other, they stay independently. However, they are connected to the top deck using what we call as a hinged joint. So, the deck rests on the hinged joint and hinged joint actually connects the bottom system to that of the top, that is the buoyant leg structure to that of the deck. Now, this is a very important characteristic of hinged joint, is that whenever the buoyant legs are subjected to lateral loading, let us say because of wave action and current, the bottom portion of the system, which is the buoyant leg structure, is free to independently behave and act. However, the rotational motions in terms of pitch, roll and yaw motions of the BLS are not transferred to the deck, because the hinged joint is capable of observing these kind of rotations. When you talk about the heave moment in the vertical plane, let us say, since the heave motion will enable the joint to transfer the load. So, on the heave degree of freedom, you can see that there is a rigid body action taking place. So, the hinged joint will be capable of transferring the heave motion from the BLS to the deck. Similarly, when the deck is having lot of superstructure in terms of cranes, derricks, etc., which are subjected to wind loading, when the wind load causes moment at the base here because of the action of the wind on the derrick or the tall structures on the deck, these rotations subsequently will not be transferred to the buoyant leg structure. It means the hinged joint plays a very important role in the whole design. Okay. So, I want to actually see whether this can be exactly modeled in the mechanical system, so that it becomes an important input variable for my reliability analysis. So, one can see here that the triceratop consists of a deck, consists of a buoyant leg structure, what we call as BLS, and of course, the hinged joint. So, I have a system, the top deck, I have BLS, maybe 3 in this case, which are now connected by a ball joint. So, the BLS can behave independently the rotations of this BLS under the wave action will not be transferred to the deck, because the hinged joints should be capable of observing this. On the other hand, when I got a superstructure, maybe a crane, maybe a drilling derrick, which is subjected to wind loading, which will cause moment about the base here, this moment action will not be expected to be transferred to the BLS. Therefore, these two systems are isolated. Okay. So, we can say that the deck is partially isolated from the BLS. However, the BLS will be connected to the seabed using tethers, which will be as similar to that you have in other compliant structures like tension leg platforms. So, these are tethers which are connecting the BLS to the deck. Interestingly, this is a form dominated system. Okay, it is a form dominated structure. So, hinged joint is actually used, is provided to isolate BLS from the deck under lateral loads. So, interestingly, it will restrain the transfer rotation displacements. So, rotational displacements are not transferred from BLS to the deck or vice versa, depending upon what kind of load is acting. For the wave load, it is from the BLS to the deck. For the wind load, it could be from the deck to the BLS. In both cases, the rotational displacements like roll, pitch and yaw should be restrained, they should not be transferred. On the other hand, it should behave as a rigid body in case of translational displacements. Okay, it should be able to transfer the heave load completely, because that is a monolithic action between the deck and the BLS to sustain the load acting on the system. Now, one can ask me a question, what is the complexity in modeling the hinged joint under the system? So, if you have a hinged joint whose rotational characteristics, what we call M phi properties, that is rotational characteristics under the given moment, need to be established, one can easily know that being a steel joint, the joint will have some specific property of M phi when it is not loaded, but the joint will have a different property of M phi when it is loaded. So, I am here looking for P M phi interaction. Interestingly, the P, which is the load on the system, keeps on changing because of variable submergence effect on the system and because of the transfer happening from the BLS to the deck. So, if you are not able to capture this behavior experimentally in a mechanical model, the input variable what you give to reliability analysis can go erratic, which will result in a wrong reliability studies. Okay. So, to ascertain this, we at IIT Madras did a very small experimental investigation on a scaled model of offshore triceratops. The mass properties of the scaled model are derived on the basis of conceptual idea. One can see here the conceptual idea was given by White et al. In 2005. A scale of 1:72 was attempted and a mechanical model was prepared based on the material availability and as far as possible to map the equivalent mass distribution that is available in the expected prototype of a triceratops. Payloads are equally distributed. To each BLS units. So, this equal distribution rather helps to maintain the desirable center of gravity on the given system. Now, the payloads which have been used in experimental study includes the platform weight, the weight of the drilling rig, the riser tension, because we are using top tension riser system for this kind of exploration, the loads from the cranes and the self weight of the cranes, the storage facilities, the mud pit, the generator, the firefighting equipments, etc. So, all these loads have been scaled up and they have been used as a topside weight on the given system. Of course, the models include the weight from the living quarters, it also includes the heli deck and pipeline systems, etc. Mass of each of the above are calculated and used in the present study. Generally, the drilling rig will be placed at the center of the deck to have a similar mass distribution, but in this specific configuration drilling rig was placed on the top of one of the BLS, so that the risers are planned to connect to the moon pool very easily on the BLS unit. So, this will help effective use of the deck space on the top of the triceratops. So, if you look at the figure shown on the screen now, which you already saw, the figure shows now the plan and elevation of a typical triceratops which is being used for the study for a scale of 1:72. The planned dimensions are shown in millimeters. You have got 3 legs of BLS, 3 legs are commissioned at water depth of 4 meters, whereas the teether leg was about 3350 millimeters, and the draft and other effective dimensions are now shown on the screen now for your understanding. So, the BLS are commissioned to the seabed through the pre-tension teethers. Ballasting is added to the system to ensure a positive center of gravity and positive buoyancy in the given design. Now, let us come to an argument of how a hinged joint need to be modeled in this case, or what should be the important input which to be fed to the reliability analysis for the hinged joint. Now, friends, please pay attention to the figure shown on the screen now. This is actually a photograph taken on the installed model of a hinged joint connecting the deck and the buoyant legs. So, one can easily see here the hinged joint has a capacity, there is a roller or a ball dress in between, you can see here. This ball dress is enabled the connection between the deck and that of the BLS to be freely rotatable. Therefore, no rotational degrees are transferred from the legs to the deck or vice versa. Now, this property of rotation in terms of moment phi characteristics of the joint need to be correctly modeled, because this becomes an important variable for the reliability analysis. Now, this model cannot be exactly studied using a numerical technique, because numerical models do not have capability of introducing variation in the moment phi characteristics of a given hinged joint under the given loading system. So, it was decided that we will capture this behavior using experimental studies during mechanical modeling. So, now it is important to estimate the stiffness of the hinged joint. Which will now have a combined action of axial force and the moment. Now, the axial force in this case is going to be predominantly high, because axial force acting on the joint now is nothing but weight of the platform, which is significantly high. So, the behavior of the joint in the absence of P will be entirely different from that of P, especially when the platform is commissioned. Obviously, you can understand now Triceratops is a positive buoyant system, where the buoyancy force very much exceeds the weight. Therefore, to commission this platform and to apply the weight on the system, you need to install the system on C. So, it is very important that the moment phi characteristics of the joint can be only estimated under the installed condition of a scaled model. So, the experimental modeling or the mechanical modeling in this case becomes very important to really estimate one of the important variable in the reliability analysis, because this is now going to tell me what will the survival safety of the platform under the given lateral loads, which is nothing but the reliability lookout of the whole system. So, interestingly, the moment phi characteristics which will govern my stiffness of the joint, which is an important variable in reliability analysis, need to be estimated using mechanical modeling. Because the joint reactions cannot be artificially incorporated in any testing facility in the joint to assess their stiffness. So, joint stiffness and damping are estimated by applying a known force near the joint This becomes one of the serious limitations in coupling the mechanical modeling with the reliability analysis, because the resistance variables considered for the hinged joint will significantly influence the failure of the platform. However, this issue is resolved during experimental investigations. The applied force is measured using a ring type load cell. Rotational response of BLS, because that is required to know the difference in the phi characteristics. Rotational response of the buoyant leg structures are measured using inclinometer. Damping is estimated using logarithmic decrement technique from the free oscillation of BLS. The moment applied per unit rotation which will give me the stiffness of the system is considered as the stiffness of the joint under operational conditions. Okay, that is very important. Now, friends, please pay attention to the sketch shown on the screen now. The sketch shows a schematic diagram to find stiffness and damping of the hinged joint. You can see here the deck and the BLS units are connected schematically with the hinged joint. We apply a ring type load cell here, where a known force is applied and the moment caused by this force is measured, and the inclinations are measured by inclinometer, and the M5 characteristics, that is moment versus rotation, are plotted, and that have been used for the study, which a typical value is again shown on the screen now. The moment rotation characteristics for a given loading under the given p value of the scaled model are estimated experimentally, and that becomes an important input for modeling this behavior of hinged joint and the actual sea state conditions, which is being used in the reliability analysis. So, friends, mechanical modeling sometimes becomes very important, and the coupling between mechanical modeling and reliability analysis will control or will influence the results of reliability analysis very significantly. Certain issues need to be actually addressed in such a manner that they cannot be simulated using a synthetic data by a simulation or perturbation techniques. For example, the behavior of hinged joint under the axial load of P, which is a dominant value in case of offshore structures, is to be estimated. The whole safety or reliability of a platform which is form dominated like a triceratop depends on the failure of the hinged joint. Therefore, the characteristics of hinged joint need to be estimated correctly, which is depending upon the actual behavior of the joint under the given loading system when the system or the platform is commissioned for a specific ballast and specific draft in sea water. So, these estimates of moment characteristics or the stiffness properties of the hinged joints and the uninstalled condition will not help in this case, because triceratop systems like triceratop are essentially positively buoyant. Therefore, when they are freely floating, the hinged joint will not depict the actual behavior of the stiffness, which is supposed to show when it is loaded or commissioned in the sea bed. So, interestingly, the variation between T0 and P under the given moment or the given rotation because of the wave action is the governing factor, which will help me to estimate the stiffness of the joint, which becomes one of the important variable to assess the failure of the joint, which is nothing but the reliability analysis focus of the whole problem. So, interestingly, in this lecture we have seen how factors are influencing the mechanical modeling and the reliability analysis coupling, and how by a simple example we understood that an importance should be paid attention to really draw important characteristics of strength or resistance of members of a structural system to really do a proper and accurate reliability analysis. Thank you very much.